In this chapter, we will be going over nuclear chemistry. As a brief introduction, let's look at the various components that make the identity of an atom and how we identify them and classify them. Let's start with the atomic number. We use the capital letter Z, and it is used to denote the number of protons that we have inside of that nucleus. Keep in mind that in the nucleus you have protons and you have neutrons, and then outside of the nucleus you have the electrons. The other identity we use is going to be the mass number. We use the capital letter A for it, and it denotes the number of protons and neutrons in that nucleus. As a shorthand notation, we use here an example, a carbon atom. We use the capital C to denote the symbol, atomic symbol. We can see the atomic number here on the bottom left. That's number 6. That means that carbon contains 6 protons. And we look at the mass number, which is 12 on that top left. And that means that carbon has both 6 protons and 6 neutrons. And you can also infer this by subtracting the mass number from the atomic number. 12 minus 6 would equal your 6 neutrons. Now, in some cases, we will encounter what we call an isotope. An isotope is nothing more than when you have a collection of atoms of the same element and they contain different neutrons. So for example, carbon can exist having 6 neutrons. This is the typical, very common carbon that we see every day. Carbon 12 we call it. It has 6 protons and 6 neutrons. But we may also encounter carbon 13 and carbon 14. In carbon 13 we have 7 neutrons and 6 protons, and in carbon 14 we have 8 neutrons and 6 protons. Keep in mind that the number of protons will never change when we are dealing with a stable isotope. The reason for this is that the number of protons will give you the identity of the element. So if we change the number of protons, we are essentially changing the element. In some cases, we'll find some isotopes that are unstable and spontaneously emit energy so that it can become stable. So it gets rid of that excess energy. When that happens, we say that we are dealing with a radioactive isotope or a radioisotope. We call radioactivity the nuclear radiation emitted by a radioactive isotope. Now, it doesn't mean that every isotope is radioactive. In fact, out of all of the known isotopes, 264 are in fact stable, so they don't really emit radiation, and 300 happen in nature, so they are naturally occurring, but they are unstable, so they do emit some radiation. In the lab, we are able to generate artificial isotopes by inserting neutrons inside of various elements, and in that sense we have a much larger number of isotopes that exist. We call them artificial isotopes. Now, when we talk about this high energy radiation, it can happen via one of 4 different types of radiations. We call them alpha particles, beta particles, positrons, and gamma radiation. We're going to talk about each of these and what they entail. So let's start with alpha particles. An alpha particle is a high energy particle that contains 2 protons and 2 neutrons. So it essentially has a mass number of 4 and it has a +2 charge simply because it does not contain any electrons. For the alpha particle, we use the symbol, the Greek letter alpha, or we can also use the symbol for helium because it has 2 neutrons, so it is essentially a helium atom, a helium ion, I should say. For beta particles, we are talking about high energy electrons, and because they are electrons, they're going to have a -1 charge, and their mass is going to be negligible or essentially 0 when compared to a proton. So for beta particles, we use the Greek letter beta, or we can use the symbol for the electron, the small e, and then the -1 to denote its charge. A beta particle is formed when a neutron is converted to a proton and an electron, so when it splits. The positron is the antiparticle of the beta particle. That means that it is the counterpart of the beta particle. And what that means is that when your electron has a mass of essentially 0, the positron will also have the same mass, but their charges are going to be different. So the beta particle will have a -1, the positron will have a +1. And we denote all of this by using the Greek letter beta and a plus sign for the positron, or we simply use the symbol for the electron, which is the small e, and a plus charge, or a +1 charge. Positron is formed when a proton is converted to a neutron. So you can see here at the bottom that equation. Lastly, our gamma rays, they are high energy radiation. They are released from a radioactive nucleus. They're just pure energy. They have no mass, they have no charge, and we denote all of this with the Greek letter gamma. Here is a table, a quick summary of all the different types of particles we are discussing, the symbol, the charge, and their mass number. When we deal with nuclear reactions, we are mostly dealing with radioactive decay and the consequences of that radioactive decay. We define radioactive decay as the process by which an unstable radioactive nucleus emits radiation. And remember that this is all with the end goal of becoming stable. A nuclear equation is very similar to a chemical equation. It can be written as such. You see here an example. You have the original nucleus, whatever you had at the starting point, is going to yield a new nucleus plus whatever radiation you lost, whatever energy, whatever mass you lost. Keeping in mind that the law of conservation of energy, the law of conservation of mass, they still apply. Right? We haven't gone into any new realms. So the sum of the mass numbers and the sum of the atomic numbers have to be equal on both sides. Here we have an example of a nuclear reaction, specifically an alpha emission. Alpha emission is the decay of a nucleus by emitting or getting rid of an alpha particle, which we had already mentioned, looks a lot like a helium atom, right, with a mass number of 4, atomic number of 2. No? So in this case, you have 92 protons, 146 neutrons, and we figured this 146 by subtracting 238 minus 92. That gives me that 146. I see my little arrow, so it's pointing towards my products. Now I have to make sure you see the numbers in blue, so 2 and 90. Okay, so 92 on both sides, 144, 2, that's 146, both sides. So in every single scenario, all of those numbers, they have to remain constant. They don't really change. Now, how do we balance an equation for a nuclear reaction? Okay, first we have to figure out what is happening, right? Let's do it with an example. Write a balanced nuclear equation showing how americium-241 decays to form an alpha particle, like those alpha particles, those heliums. Let's write first what we know, and then we'll figure out what is missing. So let's start by writing an incomplete equation with the original nucleus, so americium-241, on the left, and the particle emitted, that alpha particle, on the right. So americium, I go to my periodic table, number 95, and then 241, I got it from here. And then this 95 from the periodic table. It yields an alpha particle, which is that helium, that 4 and that 2, and I got that from the premise. So what am I missing? I'm missing all of the numbers that allow me to, on the right side, get to 241 and 95. So let's calculate the mass number and atomic number of the newly formed nucleus on the right. So I have 4, 241, so I'm going to subtract these two, and that gets me the 237 that you see here on the top. On the bottom is 95 minus 2, so it will be 93. I go to my periodic table, figure out what is the identity, what is the element 93, that's going to be this right here. Use the atomic number to identify the new nucleus and just complete the equation. That's pretty much it. That's how you write your nuclear reactions. Now let's look at a beta emission. Beta is a little bit different, right, in the fact that you don't have a helium being released. Right? Beta emission is the decay of a nucleus by emitting a beta particle. You lose a neutron and you gain a proton. If you're gaining a proton, your identity is different, so you have a different atom, right? So you have to identify that. In my case, I have, in this example, 14 and 6, so that's carbon. I know that because of that 6. I go to my periodic table and I look for element number 6, that's going to be carbon. 14 minus 6, that's 8 neutrons. My beta particle, that's going to be the high energy electron. And to compensate, to end up with the numbers right matching, so 14, 0, so it stays 14. 6 minus 1, we'll have to make it a 7, right? So that's 7 and minus 1 equals 6. So that's how I end up with this new symbol right here. That will be my nitrogen. Always making sure that what I have on the left and the right side of that arrow matches, right? Those mass, those energies, they have to be constant. Positron emission is the decay of a nucleus by emitting a positron, or that beta plus. In this case, one proton is lost and one neutron is gained. The neutron is gained. The neutron doesn't really have an effect on the identity, but the proton does. So we have to take a look at those symbols. In this example, we have carbon. Our mass number is going to be 11. We have 6 protons. That's actually how I know it's carbon. And it emitted a positron. So I have a plus 1 charge, I have 0 mass. Plus, right, plus 1 and 5, that'll give me the 6 that I'm looking for. So that means that my carbon actually became boron in this case. 5 protons, 6 neutrons, my mass number, so you can see it remained constant, and it has to, right? Now when we look at gamma emission, it is the decay of a nucleus by emitting gamma radiation. Gamma rays are a form of energy only, so there is really no change in the number of protons, so I don't really expect the identity of my atom to change through this process. So the emission causes no change in the atomic number or the mass number. So basically, whenever I have this, it's going to be very straightforward. I have my symbol, and I have my different masses, etc. Now I represent the same exact symbol plus gamma radiation. That's it. Technetium-99. M is a metastable. The M is for metastable. That means that it's really not stable, so it needs to decay, it needs to stabilize. And it does so by emitting just pure energy. Once it gets rid of that excess energy, it does become stable. It's very common for a gamma emission to accompany an alpha or a beta emission, which brings me to this very important point, in that in many cases these processes don't really happen in isolation. They happen as a combination of processes, so you may or may not see more than one thing happening at the same time in a nuclear reaction. So as a quick summary here for your reference, you have alpha emission, beta emission, positron emission, and gamma emission, and what the reaction looks like. This little table is going to be very handy when you're trying to summarize all of these processes, and you already have them here in this table. Now let's talk a little bit about half-life. Half-life is the time it takes for half of the sample to decay. Now this is important because we used half-life to measure time, simply because these processes are very repetitive, they are constant, and if you know how much you started with or how much you have at any given point, you can work forwards or backwards and figure out the different properties, the different measurements that you are trying to take. So in this case, for example, we're looking at this radioactive isotope. We started off with 16 grams, and after 14 days, we only have 8 grams of that initial radioactive isotope and 8 grams of its more stable counterpart. 14 more days, and guess what? Half of this disappeared. So now you went from 8 to 4. 14 more days pass, and you go from 4 to 2. Right, so every time one half-life passes, in this case, my isotope has a half-life of 14 days. So every time 14 days pass, half of the population changes, right? It decays, and then half, and so on and so forth. So if I looked 14 days later, I would have 1 gram, and then half a gram, and so on. Which is actually very useful for measuring things that take a lot of time. Some half-lives are a few seconds or even a fraction of a second, but other half-lives are thousands of years. This is actually how we are able to estimate the age of fossils. The half-life of a radioactive isotope is a property of a given isotope and is independent of the amount of sample, temperature, and pressure. So here are some common radioisotopes and their respective half-lives. So for example, if you look at carbon-14, it is a little over 5,700 years that half-life. We actually use that to measure archaeological dating. We can use cobalt, iodine, potassium, and you can see here that it, the number of associated with that half-life varies wildly, right? You go from 6 hours to 10 to the 9 years. So you have a little bit of everything. It really depends on the application, right? Whether it's for cancer therapy, for imaging, or for geological and archaeological dating, things of that nature. How do we use half-life to determine the amount of radioisotope present? Okay, so for example, if the half-life of iodine 131 is about 8 days, how much would a 100 milligram sample remain after 32 days? Well, we need to figure out how many half-lives we're dealing with, right? So we know that one half-life is 8 days, and we know that 32 days have passed in this hypothetical scenario. So just like we've been doing the entire semester, we are going to do a conversion. So one half-life equals 8 days. I multiply, or I divide really, 32 days by this conversion factor, 32 by 8. That's going to be 4 half-lives. So once I know that I have 4 half-lives, and I have my initial sample, 100 milligrams, so it'll be 1/2 of 1/2 of 1/2 of 1/2, right? 4 times, which is what we do here. So once I multiply 100 milligrams, my initial mass, whatever that is, times 1/2 4 times, I end up with 6.25 milligrams as my final mass, right? They got halved and then halved and so on. That's pretty much it. It's fairly straightforward. The only thing we need to figure out is how many half-lives and what is the initial mass. That's pretty much it. Radiocarbon dating, it uses the half-life of carbon-14 to determine the age of carbon-containing materials. The ratio of radioactive carbon-14 to its more stable counterpart, carbon-12, it is constant in every living organism. Once the organism dies, that carbon-14 starts decaying without being replenished, right? So in our case, we have a very specific amount of carbon-14. It depends on our mass, right? Things of that nature. But once we are no longer consuming things that have carbon, then that amount of carbon-14 starts decaying at a very specific rate, that's where the half-life comes into play. By comparing the ratio of carbon-14 to carbon-12 in an artifact or anything that contains carbon, we can estimate the age. Detecting and measuring radioactivity. This is very interesting because we don't really look at the isotope, we look at what the isotope does, right? And that's how we measure radioactivity. The amount of radioactivity, in example, is measured by the number of nuclei that decay per unit of time, right? Per second, or some cases, if it's really slow, then per minute or hour, but usually it's going to be per second. That's the international system, no? Some of the common units include the Curie or the becquerel. You have here the different um, units for it. Radioactivity cannot be detected by the senses. You can't just go somewhere and say, "Oh, this feels radioactive." It doesn't. That's not how it works. We're not able to sense it. So we do need instruments to tell us whether something is radioactive or not. Because radioactivity, even though we cannot sense it, it does have a powerful effect on the human body. It will damage your DNA. It will damage cells. Um, It kills rapidly dividing cells, such as bone marrow, skin, and the reproductive and intestinal systems. So it's super, super important that we are able to tell whether or not we actually have um, nuclear radiation around us. Cancer cells divide rapidly as well, making radiation an effective treatment for cancer. Um, food is irradiated, exposed to gamma radiation to kill any living organisms in the food. So whenever you're dealing with produce or anything that you have to move in large amounts and you're worried about contamination, radioactivity does tend to help in that regard, right? And the radioactivity doesn't just stay there once you apply it. that high energy. So that means that it's safe. Afterwards, the food is not radioactive and has considerably longer shelf life because you have killed every potential microorganism, insect, etc. with radioactivity. Several units are used to measure the amount of radiation absorbed by an organism. The RAD, that is the radiation absorbed dose, and that's the amount of radiation absorbed by 1 gram of a substance. The REM, that will be radiation equivalent for men, is the amount of radiation that also factors in its energy and potential to damage tissue. 1 rem of any type of radiation produces the same amount of tissue damage. That's important to keep in mind. The average radiation dose per year for your average person is going to be about 0.27 rem. Generally, that doesn't really do much. No detectable biological effects are noticed for a radiation dose of anything less than 25. So it has to be about 100 times the average radiation for any detectable biological effects to start being observed. A single dose of 25 to 100 rem will cause temporary decrease in white blood cell counts. If you go above that 100 rem, then you start getting radiation sickness, which is nausea, vomiting, fatigue, and all the other symptoms that accompany radiation sickness. When we talk about LD50, this symbol right here, this is the lethal dose, right? Whatever kills 50% of a population. So for example, whatever dose, if you have 100 people, right, whatever kills 50 of them, that will be your LD50. The lethal dose that kills 50% of a population for humans is 500 rem, while 600 is fatal for the entire population. So the difference between 50 and 100 is really not that much. It's about 100 rem. So it is very dangerous. That's sort of the point we're trying to drive here. For diagnosis, we actually use radioisotopes. In medicine, we use it a lot because there's a lot of properties that we can take advantage of for imaging, for cancer treatment, etc. So radioisotopes can be injected or ingested to determine if an organ is functioning properly or to detect the presence of a tumor. Technetium-99 99M is used to evaluate the gallbladder and bile ducts and to detect internal bleeding. Thallium-201 is used in stress tests to diagnose coronary artery disease. Using a scan, normal organs are clearly visible while malfunctioning or obstructed organs are not. So these are imaging techniques. These different isotopes that we are referencing here, they do emit radiation, but not to the point where it will cause damage. So it just generate a contrast in your instrument, allowing you to see better. You can see here, we're using, as an example, your liver, your bile duct, and your gallbladder. You can see the contrast, and you can see whether it's functioning or not in this scenario. Here's a few examples of where we use radioisotopes in treatment. We use xenon-133 to figure out lung function, iodine-131 for thyroid issues, technetium for bone scan, phosphorus for treatment of leukemia and lymphomas, iridium for breast cancer, and others. Now, another type of technology that takes advantage of radioisotopes is the positron emission tomography, or your PET scans. They use radioisotopes which emit positrons, as the name suggests, and they enable scanning of an organ. PET scans are useful for detecting tumors, coronary artery disease, Alzheimer's, and track the progress of cancer. A PET scan is a non-invasive method of monitoring cancer treatment. It's actually a super useful tool when you're dealing in this area of cancer treatment, etc. You can see here PET scans and Alzheimer's disease, and you can see the contrast, and they will tell you a little bit of information regarding that brain activity, glucose metabolism, and others. Radioactive amyloid binding agent. So amyloids are usually associated with Alzheimer's disease, and we can actually look at those using PET scans. Another important aspect of nuclear chemistry is what we call nuclear fission. Nuclear fission is the splitting apart of a heavy nucleus into smaller pieces or lighter nuclei and neutrons. It sometimes happens when a neutron bombards a uranium-235. Uranium-235 is massive compared to uh, most of the other elements on the periodic table. So when it breaks apart, it is able to generate more than one type of element, depending on how those protons break up. So in this scenario here, for example, you have your uranium-235, you have that neutron combining with it, and then it splits, right? Becomes unstable. You generate your krypton, your baryon, and your neutrons. Keep in mind that at every point we have to account for your atomic and your mass numbers. So 36, 56, it's going to be my 92. 235 and 1, that's 236. 91, 142, and then 1 times 3, right? So it'll be 3. That generates that 235 that I start off with. So every time, super important, we gotta make sure that those numbers are balanced on both sides. That bombarded uranium-235 splits apart, again into krypton, barium, and 3 high-energy neutrons while releasing a great deal of energy. The interesting part here is that those neutrons, those 3 neutrons that you created, they have very high energy, so they can go and bombard other uranium atoms or isotopes. And this is what we call a chain reaction. So those 3 bombard 3 uranium-235, which each one of them generates 3, so it'll be 9, and so on. And when that happens, then you have a chain reaction of nuclear isotopes, right? Nuclear unstable isotopes. The critical mass is a term that we use to identify the minimum amount of uranium-235 that we need to sustain a chain reaction, so to keep that going until you run out of uranium. A nuclear power plant uses the large amount of energy released in fission, like those neutrons with that high energy, that krypton, that barium, they're all moving really fast. So they're generating high temperatures and they boil water. They create steam, which in turn moves a turbine and generates electricity. So you don't really get energy directly from the nuclear reaction, right? The nuclear reaction generates heat, and the heat boils the water, and from there you move your turbine, right? It's kind of a stepwise process. The dangers of generating nuclear power are possible radiation leaks and the disposal of nuclear waste. So that water that has been exposed um, to that uranium, those neutrons, right? They need to be properly disposed, properly cleaned, and that tends to be some of the dangers of having nuclear power plants. Radiation leaks can be minimized by containment facilities within the power plant itself. So long as you're being safe about it and being properly containing these unstable isotopes, it should be okay. Today, most of our power plants, all of our power plants really, the waste that it generates, they just bury it. Um, we're not 100% sure that this is the best method, but it is what is happening today. Ideally, all of these isotopes will eventually become more stable and stop generating energy. But for that, it is estimated that it'll take a while, a couple thousand years. Now we talked about fission. Now let's talk about fusion. Nuclear fusion is when two nuclei, usually smaller, they join together and they form something larger. In this example here, we have hydrogen 2, which is also known as deuterium, and hydrogen 3, which is also known as tritium. It undergoes fusion to create helium, and it creates a neutron, as you can see here. And again, 2 and 3, that's 5, 4 and 1, 1 and 1, 2, 2 and 0. Right? Make sure that all of that is balanced. A neutron and a large amount of energy are also produced. Fusion is not currently usable as an energy source because it only happens at very, very high temperatures and pressure. So for these two to combine, you need to force them, right? That they don't want to combine because they're not really that unstable, and it needs a lot of energy for this process to happen. And if you're using a lot of energy, you need to be able to recoup all of that energy plus some more, right, in order for it to be cost effective. Right now it's just not. When we look at all of this through the lens of health and medicine, there's a few things that stand out. First one, and to me is the one that pops up first in my head, is going to be x-rays. They are a type of electromagnetic radiation used to form a map of bone and internal organs, which make it a good diagnostic tool for finding fractures. X-rays have been a game changer in medicine. When we look at CT scans or computed tomography scans, they also use X-rays. They create images of the body in both horizontal and vertical slices. Very good at looking at what's going on inside of our bodies, which is very positive. When we look at MRIs, magnetic resonance imaging, they use low energy radio waves to visualize soft tissue with less cellular damage than other methods. We have a similar technique in chemistry. It's called the NMR, nuclear magnetic resonance. It uses some of the same principles as the MRI. You can see here a few examples of X-rays, CT scans, and MRIs, right, to visualize different ailments, different things that we wouldn't be able to see otherwise.